As you can see from the title of this video, this is a tutorial on decomposition reactions. Decomposition reactions are the second type of different reaction we will look at as we go through a bunch of different inorganic type of reactions. The key to all of these reactions, I always try to say, is identification. And with the idea behind identification, it is nice if there's some distinguishing characteristic that is exclusive to decomposition reactions, and there is. That distinguishing characteristic is that they only have one reactant. So, if something only has one reactant, all it can do is break apart or break down, meaning decompose. Hence the name decomposition reaction. Now, even though there's only one reactant, there are actually a lot of different types of decomposition reactions. There are 5, in fact. And we're going to take a look at each one. The first type of decomposition reaction is that of a metal carbonate. And the idea behind a metal carbonate is that every single metal carbonate breaks apart in the same fashion. It always breaks apart into a metal oxide plus carbon dioxide. So as soon as I would spot a metal carbonate, I know right away that if that's the only reactant, all it can do is break apart into a metal oxide plus carbon dioxide. For example, if we looked at something like iron II carbonate. When I look at a reaction, the first thing I want to do is figure out type of reaction. So if the only reactant I have is iron II carbonate, is it a synthesis? No. A synthesis is an element plus an element. Is it a decomp? Do we only have one reactant? Yes. Then furthermore, you have to decide what type of decomp is it, and obviously we're looking at a metal carbonate decomposition. Well, if metal carbonates break up into metal oxides and carbon dioxide, iron II carbonate will break up into iron II oxide plus carbon dioxide. From here, it's simply a matter of writing and balancing a word equation then. Right? Iron II carbonate, element or compound, it's a compound. Does it have prefixes? No, which means we'll do symbols and charges and cross them. Iron symbol is Fe. It has a charge of +2 due to the Roman numeral. Carbonate is a polyion, CO3 -2. So when I cross those 2's down and reduce, I end up with FeCO3. Moving over to the other side. Iron II oxide, element or compound, it is an element. I'm sorry, it is a compound. Ionic or covalent, meaning do I see prefixes? No prefixes, means symbols and charges and cross them. Fe +2, O -2, cross those down, and you will get FeO. Last but not least, carbon dioxide, element or compound, it's a compound. Does it have prefixes? Yes. Dioxide is a prefix, so we simply write what we see. CO2, because no prefix with carbon, dioxide. Last but not least, we would go to balance this guy. So according to our rules, we keep polyions that appear on both sides. Well, I see CO3 on the left, but I do not see a CO3 on the right. So I'm going to have to break this down into each of the elements that's made up of. So I have iron, I have carbon, and I have oxygen. We have a rule that says we save H and O for last, so I will balance Fe and C first. So on the left side, I have one Fe. On the right, one Fe. On the left, one carbon. On the right, one carbon. And then lastly, oxygen. On the left, 3 oxygens. On the right, one here plus 2 more is 3 oxygens. That is a balanced chemical equation. So that's the first type of decomposition reaction. Right? The second type is a decomposition of a metal hydroxide. Metal hydroxides, just like metal carbonates, break up in a very specific fashion. Metal hydroxides always break up into metal oxides plus water. Right? So you get a metal oxide plus water. If we took a look at an example of this, we could choose something like strontium hydroxide. So we go through our regular progression. First thing I need to do is figure out the type of chemical reaction. If I look, is it an element plus an element? No, so it's not a synthesis. Is it a reaction where there's only one reactant? Yes, strontium hydroxide is the only reactant. Then I have to figure out, well, that means it's a decomp. What type of decomp? So the first thing I'll say is it a metal carbonate? No, I don't see the word carbonate. Is it a metal hydroxide? Yes, I see hydroxide, which means it should break up into a metal oxide plus water. So this will break up into strontium oxide plus water. From here, it's just a matter of writing and balancing the equation. Strontium hydroxide, element or compound? It is a compound. Does it have prefixes? No. Therefore, we do symbols and charges and cross them. So if we cross those down, you will get Sr parenthesis OH parenthesis 2. And then on the other side, strontium oxide, element or compound. It is a compound. Does it have prefixes? No. So symbols and charges and cross. Sr plus 2, O minus 2. Cross those down and you will get SrO. And then lastly, water, common name thing, it is H2O. Last but not least, you have to balance this thing. So I see SrO and H, SrO and H, so we're good there. OH on the left, I could make H2O be HOH on the right, but you're going to find out it doesn't help you, right, because you have no source of non-OHs over here. So we take a look. According to our rules, Sr gets balanced first. So I see one on the left, I see one on the right. Next, hydrogen gets balanced. 2 times H means 2 on the left. H2 means 2 on the right. We are good there. Lastly, oxygen. 2 times O on the left means 2. 1 O plus another O means 2 on the right. That means this is balanced correctly, so we have a good equation. So the first 2 types, you've got metal carbonates, metal hydroxides. Third type are metal chlorates. Right, so if I see a metal chlorate, what does it break up into? Metal chlorates break up into metal chlorides plus oxygen. So metal chlorides plus oxygen. Taking a look at an example of one like that, let's say that we had potassium chlorate. First thing I always want to do is identify type of reaction. Is it a synthesis? No, not an element plus an element. Is it a decomp? Yes, I only see one reactant. Is it a carbonate? No. Is it a hydroxide? No. Is it a chlorate? Yes. So you have to kind of go through a little checklist that gets you where you're going. If it's a chlorate, it breaks up into a metal chloride plus oxygen. So in this case, we will get potassium chloride plus oxygen. Now we need to write and balance this guy. So metal chlorate, potassium chlorate, element or compound? It is a compound. Does it have prefixes? No. So we're looking at symbols and charges. Potassium is K with a +1. Chlorate's a polyion, ClO3 -1. Cross those down and you will get KClO3. Over to the right. Potassium chloride, element or compound? It's a compound. Prefixes? No. That means symbols and charges. So K +1, Cl -1. Cross and reduce, you get KCl. Last but not least, oxygen, element or compound? It is an element. Is it a Hoberfinkel? Yes, which means we've got O2. Next, we have to balance the equation, so we take a look. Polyions would be first, ClO3 on the left, no ClO3 on the right, so I have to break them up. So I get KCl and O. According to our rules, we have to save O for last. So I look, I have 1 K on the left, 1 K on the right, so far so good. 1 Cl on the left, 1 Cl on the right, still good. 3 O's on the left, 2 O's on the right, O is not balanced. So here is an instance where I have 3 O's on the left and I have 2 on the right. Because it is the last element, you can do the half method or you can do the LCF, the least common factor. If you do the least common factor way, you're going to try to get O to 6. All right, and from there, most people could take it. I'm going to show the half method because I don't do that as often. Right? So if I want this to be a 3, I have to put 1.5 in front because 1.5 times 2 is 3. I don't like halves in my equation, so to get rid of them, I multiply everything through by 2. So here it's 2 times 1, which would be 2. 2 times 1, which would be 2. 2 times 1.5 is 3. Then if you take a look, you recheck. I have 2 Ks, 2 Ks, 2 Cls, 2 Cls, 2 times 3, 6 O's, 3 times 2, 6 O's. This equation is balanced correctly. So that's the third type of decomposition reaction. Fourth type of decomposition reaction, right, is called the decomposition of an oxy acid. Right, an oxy acid. Now, an oxy acid, just so you know, is an acid that contains oxygen. And then the second special thing that you'll have to know about oxy acids are these are the only ones, right, where you have to do the formula first and then do the name. So I must write the formula first. Right, from here out, if we get an oxy acid, oxy acids always decompose into a non-metal oxide plus water. Right? And the non-metal oxide you get by removing water from the oxy acid. For instance, say we were working with sulfuric acid. Sulfuric acid is an oxy acid. So the first thing I'm going to do is I'm going to get it out of, because it's a decomp, and the checklist you're going through is it a carbonate? No. Hydroxide? No. Chlorate? No. You get it into the old name, which means this would be hydrogen sulfate. Now, according to this, we're going to break up into some nonmetal oxide plus water. Here's the catch. Nonmetal oxides are nonmetals. They get prefixes. There's no way I could know what the prefixes are. That is why I have to write the formula first. So if we were to do this, hydrogen sulfate is a compound. It does not have prefixes, so you do symbols and charges. H plus 1, SO4 minus 2, and you get H2SO4. You know water, H2O, is a product. So to get the nonmetal oxides formula is you simply remove 2 H's and 1 O from this formula. So if I take 2 H's away, there's none left. If I take 1 O away, there's now 3. The nonmetal oxide would be SO3. Then you go back and name it. SO3 would be called sulfur trioxide. And then lastly, you would balance this, but you'll find this was already balanced. Right, so oxy acids are unique in the sense that they are the only ones that you have to write the formula first. The rest, we can always get the words and then write the formulas. Last type. And this would be letter E, called binary. Right? A binary decomposition, right, for lack of a better description, is all of the others. Right? It always is not one of the other ones. Binary always break up into an element plus an element. So the reason I have the checklist is to eliminate everything to arrive at the fact that it might be this one. For instance, if I saw something like barium bromide, the first thing I would do is try to identify the type of reaction. Is it a synthesis? No, it's not an element plus an element. Is it a decomp? Is there only one reactant? Yes. No plus sign over here means it's the only reactant. So then, what I do is I go through my checklist. Is it a carbonate? No. Is it a hydroxide? No. Is it a chlorate? No. Is it an acid? No. If you say no to all those questions, all it's going to do is break up into the 2 elements that makes it up. And barium bromide is made up of barium and bromine. And then from here, it's just writing and balancing. So, barium bromide is a compound. Is it prefixes? No, so that means symbols and charges. Ba is in group 2, so it's a plus 2. Bromine's in group 17, so it's a minus 1. So you get Ba, Br2. Over to here. Barium, element or compound, it's an element. Is it a Hober-Finkel? No. So it's just Ba. Bromine, element or compound, it's an element. Is it a Hober-Finkel? Yes, which means it's not Br, but Br2. Lastly, you have to balance this guy. Right? So 1 Ba, 2 Brs, 2 Brs. That is balanced correctly. So 5 different types of decomps. The way you know it's this binary type is that you've eliminated all the other ones. It's not a carbonate, it's not a hydroxide, it's not a chlorate, and it's not an acid. Therefore, it just breaks up into the 2 elements that you see. I hope this helped out in keeping things in order with your decomposition reactions. By far the most complex in terms of amount that you have to remember. But hopefully this straightened you out. As always, if it didn't, please feel free to come in for some help.